We'll move towards our 10th session on the 5th day by Mr. Rahul Kharar, co-founder and CTO at REST-ET AI, Bangalore, Karnataka. The topic is navigation energy challenges, the role of emerging technologies in India's sustainable future. So, without wasting the time, I request Mr. Rahul Kharar to please proceed with the session.
Yeah, thank you. So let me begin. Let me share my screen and then I get started. Just give a bit. Just 1 minute. I'm just setting it up.
Sure, sure.
Okay, fine. Can you all see my screen? Okay.
Yes. But it's saying this is no longer
active. Yeah. Just 1 minute. I'll try it again. There is some problem. Yes, it should be now. Yeah. Okay. So today I'm not sharing any slides. I'm going to give you an hands-on and little use cases, right? Because our topic today is navigating energy challenges, the role of emerging technologies in India's sustainable future, right? So we'll start with a little recap. We did talk about personas in AI space, right? And when we talk about emerging technologies, there are a lot of technologies that will help build India's sustainable future. But our focus today would be AI. That's my expertise, and I'm practitioner of AI. And there are other technologies like AR, VR, and then upcoming technologies like quantum computing, which will help solve problems like combinatorial optimization problems. And then there are technologies like IoT and edge computing, which is basically an enabler to solve AI problems, right? IoT and edge computing basically helps you get the data from various devices and machine, and which data is very valuable to build models which can help you basically optimize your energy consumption, right? So there are many peripheral technologies which will also be useful, but our central focus would be AI as an emerging technology that will help in India's sustainable future, right? Now, why do we need to build data-driven model, right? That's the first question that we should answer. Why data models, right? When we have a scientific model, right? What we call them as domain-driven models, right? Like for example, if I am solving a heat transfer problem or a fluid mechanics problem or even a civil engineering problem, I do have science-driven models or domain-driven models. What are these domain-driven models? For example, if I'm solving a fluid mechanics or heat transfer problem, the scientific rules that I need to comply to are, say, Navier-Stokes equation. I need to balance mass, momentum, and energy. And then only I'll say that my solution is converged, and that is conforming to the science, right? We have domain-driven models. But when we have so strong domain-driven models, which are being used for so many years by so many people, then why do we need data models? Uh, if many of you might be from mechanical engineering, right? They might be doing CFD, computational fluid dynamics. So when we have equations like when we have solutions which can be derived from Navier-Stokes equation, still we do CFD, right? Why do we CFD? Anybody? Or maybe for that matter, stress analysis or CFD. Why do we do that? When we can solve using basically the fundamental scientific equations. So there are n number of reasons. One of the reason is, for example, if you want to simulate a particular geometry at a sub level, right? I think someone was answering in chat. So there is no PDF slide. I am sharing my screen where I'm going to use it like a whiteboard today. I'm not going to share any slides, right? I'm more of a blackboard guy. But don't worry, I'll write most of the things when I go forward, right? I'm just giving you a background and introduction, right? We were at CFD. So why do we CFD, right? So for example, if I want to simulate a flow inside a pipe, so I can use my basic scientific heat transfer equations and fluid mechanics equation to calculate pressure drop or to calculate average velocity inside the tube. But what if I want to know velocity at different zones within the tube, right? That's where CFD helps me to discretize that geometry to whatever level I want to discretize, and then get the velocity and pressure values at each cell level, right? And those are important in many, many use cases. Like when I was at Thermax, we used to have one problem of flow distribution in our thermic fluid heaters. During turning, when flue gas was turning from the reversible chamber,
Hello.
the flow distribution. Yeah. Can you guys hear me? Am I audible?
Yes, you are audible. Yes, you are audible. Please continue.
Okay. I think someone was, yeah. Okay. So we had a problem during flow distribution problem in the reversible chamber and because of the flow distribution, there were tubes failing, right? And this was solved using CFD, because CFD help you understand the flow distribution at the component level, and it help you measure the velocity in the reversible chamber, which were very high, and because of the higher momentum, the flow distribution was not uniform, and because of non-uniformity of flow distribution, the velocity at one side was very high compared to the other side, and it was hitting the tubes. And because the fuel used was coal or solid fuel, it has small ash particles which are very abrasive in nature, which hits the tube and tube gets filled, right? So basically, fundamentally, what I'm saying is, even before AI, we used to solve problems using CFD and FEA, right? To break down the problem into smaller components so that we understand the the required characteristics of that, whether it is about stress characteristics or flow characteristics at a very subcomponent level, which was very important to understand the problem at at a very small particulate level. Now, just extending that thought, right? Now, when we do CFD, I have seen people struggling even to match pressure drop.
Rahul, excuse me.
Yeah.
The board you are writing on, we are not able to see it. Actually.
No, I'm just calling it out. Sorry. Pressure drop. Okay. I am not writing it. Achha, you're not able to see the board itself, you're saying?
Able to see the board itself.
Oh, okay. What I'll do is instead of writing, I will type it out. That will be better. Just give me a minute. Just give me a minute. It is better I use presentation. It's not working. Okay. So what I'll do is I'll just type it out instead of that. Right. Okay. So what I'm saying is to simulate fluid flow inside the tube, inside a plain tube, and to just simulate laminar flow, right? Laminar pressure drop inside plain tube to simulate pressure drop using, say, Fluent or ANSYS software. Even this becomes difficult many times. Why is that? Have somebody of you tried simulating, say, for example, capturing friction factor as 64 by RE, which is basically the value of friction factor when the flow inside a plain tube is laminar. Have you tried replicating this using any CFD software? So, for example, if you have a 2 meter length tube and you try to replicate this friction factor value, which we know that it has to be equal to 64 by RE, and many times, or most of the times, you will not get that value. Why is that? Does anybody know? If you try to get this value using any CFD software, whether it is Fluent, ANSYS, or any other, say, OpenFOAM, any software, you'll not be able to replicate this value. And even though it is a proven thing that for laminar flow, your friction factor should be equal to 64 by RE. Does anybody know why you are not able to achieve that value using CFD software? You can achieve, but in the first run, you'll not be able to achieve. So what is the problem there? Anybody knows that? So the problem is basically whatever equations that we have built over a period of time, right? There is a fundamental assumption that your flow is fully formed flow, right? It is for a fully developed flow. The equations are for fully developed flow. But now, when you are solving real life problems, right? Fully developed flow is the fundamental criteria. So now, when you are solving any problem using CFD or any in practical cases, right? Say, for example, if you are trying to simulate a boiler, and boiler, maybe your tube length can be even 1.5 meter, depending on what type of boiler and the size of the boiler or the capacity of the boiler you're talking about. So sometimes 1.5 meter length will not be enough for the flow to be fully developed. So your equation, which is an algebraic equation or an empirical correlation, which we have learned for so many years, doesn't stand true for this particular tube length. Then what do we do? If I have to capture, if I have to replicate, say, friction factor for a 2 meter tube, which should be equal to 64 by RE for laminar flow, how do I do that? So there are two ways of doing it. One is, what I'll do is I will take the output of my first pass. Again, I will feed that output into the same tube till my flow is fully developed, and then my friction factor will match. That is one way of doing it. Second way of doing it is I will take 2 points within the tube. Like, for example, if my tube is of 2 meters, right? Like, for example, my tube is, say, 2 meters. So I'll take 2 points in between. Say, for example, I took 1 point here, and then I took another point here, and then I will capture friction factor between these 2 points, right? Instead of taking the geometry, I'll capture the relative pressure drop between the 2 points, and I back calculate the friction factor. This also helps you understand what is my relative pressure drop between the 2 points, and this will help you match the friction factor. And why I'm telling this is basically, in real life, like your algebraic equations or the empirical correlations that are coming from your domain always doesn't stand true for real life use cases, because there are a lot of assumptions when we talk about empirical correlation. Like, fully developed flow is one of the assumption. Like, for example, if I'm designing a boiler for Indonesian coal, there are different type of coals, right? Indonesian coal, Indian coal, and the characteristics of each fuel is very different, or this coal is very different. Now, if you have designed it for certain characteristics and the characteristics on the ground are different, you're not going to get exactly similar results what you have designed it for, right? So in natural environment, the things are very different, which you cannot take into account each and every scenario while designing those, right? And that's why when you go to real world, when you go to actually practical world, the whatever you have designed it for, it will always be some plus or minus. That's one thing. The second thing, again, I'll talk about boiler industry because I have very closely worked with the boiler industry. In boiler industry, there is a term called seasonal efficiency. Now, what is seasonal efficiency? basically, say for example, if I installed a boiler today or deployed a boiler today, and my efficiency today is say 90%, right? And my maintenance schedule is say 15 days. So maybe on 14th day, I am getting an efficiency of 85%. Why? Because I have not cleaned or maintained the boiler for last 14 days. There might be n number of reasons my efficiency had dropped down. One is maybe there is an ash collection inside the tubes. There might be ash in the flue gas chamber. There may be slagging happening inside my furnace walls. So because I have not maintained it for last 14 days, my efficiency will drop down from say 90% to 85%. And on 15 day, when I clean the boiler, next day my efficiency will again increase, right? So this we call it as a seasonal efficiency. There are different terms people use. One of the term is seasonal efficiency. Basically, this is like a season from maintenance to next maintenance. Your efficiency, as soon as you maintain the boiler, or rather you clean the boiler, your efficiency goes up, and then over a period of next schedule, it will drop down depending on what conditions you are running it on, right? So this seasonal efficiency also plays a role in your energy consumption, right? Because your efficiency is dropping down, that means your fuel consumption has increased over a period of time, over a period of those 14 days. So how do you solve this problem, right? This is an dynamic problem. We have designed it for one condition, but you are seeing that for next 15 days, your efficiency is dropping down and your fuel consumption is increasing, right? Why I'm telling you all this? This is basically to emphasize the importance of data-driven models. And data-driven model is nothing but AI, right? So with the domain-driven models, you might have designed your equipment, but data-driven model will help you simulate the actual readings. Like for example, what is happening at my site in practical, and that the model built using data will help you fine-tune your particular component, whether it's a boiler, whether it's a compressor, or whether it is some other domain problem, like any other domain you can pick up, even a business problem also. You can fine tune the parameters of your problem statement using data driven models, which could not have been possible only using domain rules. Because domain rule is basically nothing but our experience and the science, right? In heuristically, you can do only so much. Once you have exhausted all the possibilities that you could have achieved from your heuristics or domain driven models, that's where data driven models comes into play, wherein data driven model will help you further enhance the efficiency of the system dynamically, right? You're with me, guys, right? So there are two types of systems. In business also, we call it two types of systems. Let me give you an example of business. And again, energy saved, like there is a saying, right? Energy saved is energy generated, right? If you are able to save energy, that means if you are able to increase the efficiency of any equipment or any process, it can be a very small saving also, but cumulatively the effect would be very huge, right? And that's why we say why emerging technology will help you one component of the energy problems, right? Which is basically it will increase or enhance the efficiency of energy. The other day we were talking more from supplier and more at a macro level. Today I'm talking about more at a micro level. You pick up any problem statement. If you are using, say, any emerging technology, our focus today is again AI data driven model, you can save energy, or you can save the energy or fuel consumption or the energy consumption by your design using data driven models, and that saving will lead to basically uh, um, um, say for example, if we are saying that coal is going to it's not, we don't have infinite energy, right? When we talk about coal or petrol or diesel or furnace oil, there is finite resources of this energy, so we can prolong the usage of coal to more number of years by increasing the efficiency of all this equipment which we are using. And the alternative way of you further enhancing this is use of renewable energy sources. But that's an alternative way of doing it. Like instead of using fossil fuels, you're using alternative fuels which are cleaner in nature and which are natural in nature. But again, there are its own challenges, right? When say for in colder countries you don't have solar energy so much. So how do you solve that problem? We'll not get to that. Our topic is whether we can use emerging technologies to navigating through energy challenges. Yes, we can. And how we can is basically complement your domain-driven models using data-driven models. And that's where the usage of data-driven models becomes very important. And that's why we need to learn how we can use data-driven models and how they can help or augment your existing design techniques, right? So that's the whole background of how emerging technologies can help navigate through energy challenges. Now, let's talk about use cases, right? Let me a new slide. So let's talk about use case. Let me pick up an use case, say throughput, right? Or maybe downtime. Let's start with downtime because we were on maintenance, right? So again, I'll give an example of boiler. If you guys have some other example, feel free to interrupt me and we can get into conversation of some other domain as well. But boiler is, and I hope everybody knows boiler, right? Boiler is a pressure part equipment, very well known in mechanical folks would know very much. Rather, other people would also know about the boiler, but boiler is basically a pressure equipment which is used in many industries. It is used in textile, food, energy. It is used in tea. So every process industry requires steam for their heating purpose, and that's where boilers are used. And then there are other heat transfer equipments like thermic fluid heater, which is alternative to boilers, depending on what type of use cases we are working on. Now, why downtime, right? So I'll tell you. So whenever a component is sold, whenever an equipment is sold, whether it's a boiler or for that matter, whether any domestic equipment is sold, there is a fixed maintenance schedule they talk about, right? Like for example, even if you're buying a water purifier, right? There is a maintenance schedule, like for example, of 6 months. 6 months, like for example, if someone is buying AquaGuard or Eureka product, the maintenance guy will come every 6 months to replace some components or to maintain your equipment. Similarly, in B2B space, if you're selling a boiler or any other industrial equipment, there is a fixed maintenance schedule which is part of your manual, operations manual, when anything is sold, right? But you can relate to this, right? Like for example, if I am buying AquaGuard at my home versus some other home, say for example, today we are three in our family in Bangalore, right? Like for example, if I go to my hometown in Aurangabad, there we are around 8 members who are staying in one house, right? So the consumption pattern of same AquaGuard, if I have a same AquaGuard here in Bangalore versus the same AquaGuard in Aurangabad, the consumption pattern is going to differ, right? But still, as a standard practice, the company has provided me 6 month maintenance schedule. Now imagine if it is similar maintenance schedule of the same AquaGuard, and you can relate this to boiler also. Your efficiency of water cleaning or cleaning whatever the filter efficiency, or you can call it any component efficiency, is going to be very different at both the places because it is being more used in Aurangabad rather than in Bangalore. Similarly, when a boiler is sold, we sell it at a fixed maintenance schedule. But depending on the load on that boiler, type of fuel, definitely depending on type of fuel, we maintain different maintenance schedule. But depending on load pattern, which could be very different at different plants, the efficiency will differ and the operation will differ. But when we are giving a static maintenance schedule, that means some people or some plants are operating boiler at a very high efficiency and some plants are operating that boiler at a very low efficiency, which is not correct, right? Because the plants which are operating that boiler at a very low efficiency are going to consume more energy in the form of whatever, right? Energy in the form of fuel, energy in the form of electricity, energy in the form of water also, right? Because water consumption will also increase due to scaling or whatnot. So how do we solve this problem? Because same boiler, same maintenance schedule is going to different plants, but because plant inherently may have different load patterns, that's why your maintenance schedule should vary, which does not vary. So we can call it as a preventive maintenance. You might have heard about this preventive maintenance quite frequently in AI world when we talk about manufacturing, right? Which is very much similar to downtime, right? Because if you don't maintain it on time, your downtime will increase, your failures will increase. So how do you reduce your downtime, right? That's where data-driven models comes into picture, and we have solve this problem for many manufacturing industry. I'll give you one example, right? So imagine I am again. Let's take another example. Let's take example of fine blanking press. In fine blanking press, there are various process parameters like in feed, speed, blanking force, which are and these parameters are set at different operating conditions. Like speed can be set as a different operating condition, blanking force can be set at different operating condition to manufacture a particular item, right? So this, and then there are many other process parameters. Similarly, if you are running a boiler, there would be n number of process parameters which would be set to run that particular equipment. Now, from a design perspective, you are already given some standard readings. But when you are running practically for a different item and at a different operating condition, you will adjust those parameters heuristically. And heuristic comes from science, right? Heuristic is nothing but what comes from experience. And you have achieved a throughput of, say, X. You have achieved a throughput of, say, X using heuristics. Throughput of X using heuristics. And heuristics, I will say, equal to science. Heuristics is nothing but experience, right? And experience comes from your domain knowledge and also from what you have seen in the past. So you would have set these parameters based on your experience and based on your scientific knowledge about this equipment, and you have achieved a throughput of X. Now, are we saying that beyond this I cannot increase the throughput? No, it cannot be, right? So you might be using dashboards, right, in your day-to-day life. You are all faculty members. You might be using some sort of dashboards, like some sort of screens, for example, to understand the profile of your students. I'm just making it up. I don't know how that is being used, but say, for example, there is a dashboard on different subject marks of each student, right? And there are 3 graphs. How much he or she has scored in, say, heat transfer, how much he or she has scored in fluid mechanics, how much he or she has scored in mathematics, or how much he has scored in some, say, other subject, right? Some machine tool subject or operation research subject. Now, humanly, I can comprehend maybe 3-4 graphs at any given point of time. But if I have to comprehend like say heat transfer and fluid mechanics combination, maths and this combination, humanly you cannot do that. And say, for example, you want to come up with some portfolio score of a student. What I will do is I'll try to build a model which humanly I cannot comprehend. Say, imagine now you generally in engineering you'll have 40 subjects, right? Imagine I want to look at the marks of all 40 subjects and make out some pattern that when this combination of subject or of if student is scoring on this combination of subject, they are likely to do well in certain type of jobs. Like this is my problem statement, imagine. And similarly, analogy to a downtime problem is that if I have this combination of parameter, like my infit speed is say 2 meter per second, blanking force is say 8,000 Newton, and then so on and so forth. For this combination of parameter, I am achieving a downtime of say 60 minutes, or I am achieving a throughput of say 60 units per hour, whatever my outcome metric is. So heuristically, what I'm saying is when you are looking at graph, you may consume as a human, you may consume 3-4 graphs at any given point of time. But now here I'm talking about when you are looking at a student profile, you're talking about 40 subjects. Can I comprehend 40 subjects for n number of students at any given point of time? As a human, no, I cannot. So can I build a model which will help me identify those patterns and then help me get to that score? Like for example, you have one row of values. What we'll do is say insert table, right? So you have say subject or name of the student, subject 1, subject 2, subject 3, and say portfolio score. We'll call it portfolio score. Some fancy term, right? And you are filling this for each student. And now imagine these subjects are 40 subjects, right? And what I was saying that if you have graphs of these 40 subjects, you cannot comprehend. Now what I'll do is this portfolio score is nothing but say, for example, we have some data collected wherein people have gone to a company above certain threshold or a very good companies, and they have done well in those companies, right? And I'm giving this analogy. This analogy can be applied to downtime, throughput, any problem. It's basically data where these are your independent variable and this is your outcome variable. So in terms of downtime, here it will be say downtime, time to downtime will be our outcome variable, and this will be our process parameters. Similarly, for throughput, this outcome variable where I have written portfolio score, it would be units per hour, for example, units manufactured per hour. So what we can do is once I have arranged this data, I can build a model, and model will help me identify that when this combination of subject has an average score of more than say 60 marks, generally students have done well in their career. I'm just making a very hypothetical problem statement, but just to make you understand how models are built, which humanly or heuristically we cannot identify those patterns, right? So similarly, for downtime, what I do is I collect all the historical data. Like for example, if I'm running that machine for last 6 months, I will have 6 months data, wherein at different process parameters for different items are nothing but name in this case. I will collect that data, I will arrange that data, and I'll try to build a model using any machine learning technique. Even say you can call it even linear and logistic regression is also machine learning techniques only. Though we call them stats because they have been used for many years, and that has been extended to advanced techniques like say random forest model, decision tree model, gradient boosting model. Those who have learned AI, they would know about this model. Those are basically advanced ML models which are used to identify patterns in the structured data. Structured data is what? Tabular data. So once you have such type of data, I can identify patterns in my historical data which has led to higher throughput, or which has led to lower downtime, or which has led to reduced energy consumption. It can be any problem statement. You can build an ML model, and once you build an ML model, it will give an understanding that generally when this process parameter in feed speed is say greater than or is in between, and this, don't worry about these absolute numbers, right? It is just to make you understand, say 1 mm per second and 2 mm per second, and blanking force is in between say 1000 Newton and 1500 Newton. Generally my throughput is greater than say 5000 units per hour, which is say for example my average is 4000, and with these settings, generally what I identified from my machine learning model is the that when this combination of process parameter, and here I'm talking only about two, but in your actual machine the process parameters could be 20, or rather in practically when we have solved this problem for our blanking force, the parameters were more than 20. So it helps you identify such combinations which will lead to higher throughput. And then now whenever I am running this item, and whenever there is possibility that I can keep my blanking force between 1000 Newton and 1500 Newton, I should do that. What will and it will also tell you, like for example, your input parameter, like I told you, right, in the beginning, when I start using the boiler, my efficiency was 90%, but at 14th day it came down to 85%. So one of my variable could be even runtime, right? So for runtime of, I can get something like this also from my data patterns for runtime of, or maybe units per hour is equal to function of runtime. If I get this, and units per hour are also function of process parameters. So once I get this, I also know that when my runtime increase. So for example, when I moved from one day to second day, maybe I need to set from 1000 Newton to 1200 Newton to achieve my same efficiency. So what I'm saying is, even though my seasonal efficiency was dropping down, but with time, I got to understand that if I am running from, say, if I ran it for first 5 days, on 6th day, my setting should move from 1000 Newton to 1200 Newton to achieve the same efficiency.
Even such insight you will get. So what essentially you are doing is, now your seasonal efficiency, which was dropping from say 90 to 85%, it might drop only from 90 to 88%. So imagine if this 3% gain for every 15 days, what will be the gain in 1 year? And if you cumulatively calculate the gain of fuel saved, water consumed, and everything, energy consumed, it will be huge difference. So basically, again, going back to what we started with, right? Even though when you design, like for example, CFD was the one of the best example, right? That we started using a long time back, CFD or stress analysis. These were also data-driven model because these are numerical techniques, right? Built on top of domain understanding. AI is extension to that, right? You are taking, instead of you're trying to simulate, you're taking real world data. There, what you do is you simulate. You take boundary conditions, you apply boundary conditions on different boundary conditions. You try to simulate the behavior of a given equipment. In AI, the difference between CFD and AI is there you do simulations. Here you are actually taking real life readings and then converting that to a model to identify patterns, right? But in both cases, you are basically trying to simulate the real world into virtual environment, right? In one world, you are actually running simulations. In other world, you are actually taking the real world data. But the underlying logic is to identify the pattern and to understand how my component or system behaves so that I can operate it at a best possible optimal conditions. That's my underlying objective, whether I'm doing CFD or whether I'm doing AI. And CFD has helped me a lot to get into AI later, but that, because you got my introduction last time, right? I started my journey with Thermex, where I used to do a lot of thermal and fluid calculations and CFD. And eventually I went into AI and start solving other domain problems like banking, financial, healthcare, telecom, media, and other sector. But if you really look at the underlying fundamentals, it are all same. When you are building a data-driven model, whether the data is coming from heat transfer or fluid mechanics equipment, or it is coming from banks, it doesn't matter. The underlying pattern recognition system or the underlying techniques that we use, underlying fundamentals that use, that stays the same, right? So that's where we are. Like, I'll repeat, right? So when I design an equipment, whether I'm designing a boiler or whether I'm designing a washing machine or whether I'm designing a water cooler or whatever I'm designing, I'm using science fundamentals to design that equipment. Then I am using, say, CFD to optimize, to understand different scenarios proactively, right? Yet I have not ran and given it to deploy somewhere actually. So before that, I do CFD to understand different simulating conditions and I optimize my parameter and I give it to deploy it at some site. Now, when it is running on site, that is actually running in actual environment. And then there are different uh, parameters that plays a role. Even the runtime plays a role. Even the load pattern plays the role. Like for example, domestic equipment I talked about, right? Something like AquaGuard. When you have a family of 3 members versus 6 members versus 8 members, your consumption is going to change. But if your maintenance schedule is same, that means you are operating that particular equipment at a lower efficiency than it should have been. So how do you solve this problem? There could be a data model in your edge device. Edge device is nothing but you can run ML model at the edge itself. Edge is nothing but in the component itself. Can that edge device or can the ML model and the component itself help me fine tune the parameters to stay at the same efficiency? Yes, we can do that. But there is always like, right? Energy is always converted from one form to another. It's like not you cannot have a machine which is helping you stay at the same efficiency, but there is no energy consumption from other side. So that's where optimization comes into picture. Like for example, if I say I can maintain the same efficiency for 8 member family and for 3 member family, there will be some sort of compromise at another end, like some sort of compromise at the electricity level or some other form of energy, right? It's not like nothing is free. If you are trying to achieve something at the same level, their energy has to be consumed from somewhere else. You need to know from where I am consuming that energy so that the overall ecosystem is basically efficient. It is not one system in isolation is efficient and you are burning something elsewhere, right? There is a big debate or there is a lot of research going on using electric vehicles in India versus say Western world, right? Because our major source of electricity in India is coal, right? Now, for example, if I'm running today my electric car in Bangalore, it's very clean, right? Because it's an electric car. It is not using any fossil fuel. But then to generate that electricity, I have consumed coal at some other place, right? So my source, it might be burning more fuel. So we need to understand the dynamics. Like overall ecosystem should save energy. It's not one equipment in isolation saves energy and you're burning something elsewhere, right? So that's where when I'm saying when we design this equipment, at least to a certain level, we should understand that whole ecosystem that I'm optimizing the energy for. And that's where, because you are optimizing it for ecosystem, the variables into play are huge number. For example, imagine I am optimizing it for aquaguard. So the variables are number of people, the variables are the process parameters within the aquaguard, the variables are environmental conditions of different geographies, whether it is Bangalore or whether it is Aurangabad or whether it is Sambhajinagar, right? So there are different variables which are into play, and humanly identifying the pattern with so many variables is not possible. That's where data-driven models comes into play. And in data-driven model, when it's a data-driven model, there is no limit on how many variables you can you have, right? You can build a model for even 1,000 variables, right? Only given condition is you should have enough rows. You understand degrees of freedom, right? So imagine you have 10 columns and 10 rows of data. Can you build an ML model? So let's get into statistics. So you have 10 rows and 10 columns. Can you build an ML model? Or what type of model you will get with 10 rows and 10 columns? So basically, see, when your number of variables are equal to number of columns, what you get out of it is exact solution, right? ML models are all probabilistic solution. It's an optimization problem. In optimization problem, your number of rows has to be more than number of columns. Then only it becomes an optimization problem. That means your each variable have multiple degrees of freedom to play with. Then only it becomes an optimization problem. If you have same number of rows and same number of columns, then that is an exact solution. That is only one combination of variable set that will help you achieve that objective. Then there is no optimization there. Only when your number of rows are more than number of columns, then only it becomes an optimization problem, right? Now, how many more number of rows you need, that all depends, right? Like for example, if you are building a regression model and what does Z statistics tell us? Z statistics tell us that at least one column should have, or when we are talking about one variable, we should have at least 30 data points to identify the pattern, right? Like for example, you might have done that in your research when you do sampling, right? At least you need 30 data points. And if you are doing TE stats, you need at least 5 data points. And now this is only at one variable level. So you can have a thumb rule, right? For example, if I have 10 columns, I should at least have 50 rows to build a model. If there is something less than that, you will exhaust degrees of freedom. So what I'm saying is, you can have as many number of columns as you want, given you have enough number of readings. Readings are nothing but number of rows. And if you have enough number of readings, you can build and study any combination of parameters that you want to study on. Whether you are solving a downtime problem, whether you are solving a throughput problem, whether you are solving an energy consumption problem, you can solve any problem. And what will help you? So there is a design stage. Let's recap, right? There is a design stage. Which is say function of domain and experience. Experience is nothing but heuristics. Then there is a simulation stage, which is a function of, say, I'll call it numerical methods, right? Where you can do simulations, like something like ANSYS and stress analysis. Different field have different softwares. And then there is a data-driven model stage, we can say. The AI stage, you will say. These are all our terms, just to give you an understanding of how these things will work. Function of data, real world data. Right? So when you are designing any equipment, you start with domain, design, science. then you can further optimize those settings using some softwares like CFD and all that, which are numerical methods, basically simulating with the different scenarios and different boundary conditions. That's where that's what we can achieve in the first two stages. Third stage is when we have collected enough real world data, when an equipment is running for some period of time, whether it is 1 month, 1 year, it doesn't matter. You have a lot of data, and that data can be used to further understand the real world patterns, how my machine is behaving and under different operating conditions. And then machine can be anything. And it is not only related to, let me tell you, you can save energy even making business processes efficient, right? So when we calculate ROI, if I am giving an AI solution even for invoice processing, imagine, can I incorporate some sort of sustainability element into it? Yes. How? The other day I talked about, right, who is the best agent, and I talked about that human is the best agent when human is using its own resources, like its own mind, its own hands, its own legs, to solve a particular problem. But as soon as humans start utilizing externalities, whether in the form of laptop, computer, desktop, electricity, calculator, and whatnot, it is using external energy resources, right? Now, if I am deploying an AI solution, and if I do carbon consumption calculation, some sort of carbon calculation, then there are websites available who gives you uh, uh, CO2 or carbon, some carbon score websites are available nowadays. Whatever equipment you use, how much, what is your carbon rating, right? You can get that carbon rating for each task against which you can simulate your AI usage, and you can even have an ROI with the consumption, not only in terms of money investment, but in terms of energy investment also. So you can incorporate sustainability into calculation, into ROI calculation as well, which will be very important going forward. Many people are talking about it. Like, for example, this sustainability scores or carbon credit scores or other scores are going to be very important for many financial decisions also, right? So coming back to this, it is not only important that we are talking about only energy equipment or physical equipments that will help save energy. You can save energy even in your day-to-day transactions as well. Like, for example, if you are doing some communication, imagine if you are using ChatGPT, and if you are using ChatGPT to write an email, whenever any prompt that you give to ChatGPT, there are a lot of GPUs running at that data center which are consuming a lot of energy. Even Sam Altman talked about it, right? If you run one research report, one glass of water is lost and whatnot, right? Why I'm giving this example is, we as a consumer should also understand where we should utilize such sophisticated equipment which are very energy hungry, and where we should not utilize those. But consumer may not do that. So as a designer, right, we are, from that day, we are mostly into the shoes of either research persona or application developer persona. India is called an application capital. So most of the work that will happen in India is more on the application side, right? Because there are very few initiatives where we are talking about we ourselves build LLM models or so on. But there are many initiatives where we are talking about where we are building applications for whether business or for other science domains, right? So if India is going to be an application capital, we as an application designer should know how to design our equipment, which is not only efficient from a business perspective, but also from an sustainability perspective. And as soon as we design our equipment from a sustainability perspective, your gains are enormous, right? Because energy cost is going to increase only with future. It's not going to go down, because more the energy demand increase, even from the technology side, it is going to go up and up. It is not going to go down. So the more your design is energy efficient, along with the business efficiency, your design is going to sustain for long. I'll take a pause here. Any questions till what we talk about, right? So idea is to help you understand why emerging technologies can help at very different fundamental levels. It is not only about whether you are solving a science problem. It can be any problem. It can be a logistic problem. It can be a supply chain problem. It can be a business transaction flow problem. Because if you go to the depth of each and every problem, there is energy consumed at different levels. Only the scale of energy consumption would vary, but there is an energy consumption happening. And if you keep in mind, as one of the cost function is your energy saved. So, for example, what essentially we do when we calculate ROI, when we design anything, right, there is always an objective function. We can call it a cost function also. So whenever you are designing it for certain objective, whether it is for business objective, whether it is for ROI objective, whether it is for energy consumption objective, and if you add an energy consumption element into that objective function or cost function, you'll optimize for energy also. And one of my friend is working on this PhD topic, where when you're running or when you're building an ML model, you're not only optimizing the underlying function to reduce the or to increase the entropy of the error, but you're also optimizing for energy consumption. So people are introducing energy into cost function itself, energy consumption into cost function itself. So there are a lot of research happening on this area, right? So I'll take a pause here. Any questions around what we discuss? Feel free to ask. See, yeah, go ahead. Sorry, someone is asking something.
Hello.
To
Yeah.
questions, you can post it in the chat box also.
Okay.
There's one question from Mr. Rohan.
Yeah.
Hello.
Yeah. Please
Can I
go ahead.
Hello.
Yeah, go ahead.
Sir, can you please suggest me some numerical methods regarding the same? And if the numerical methods are useful, and these methods are required to check first of all assumptions or not. If it is needed to check the assumptions, so then which kind of assumptions we need to check it first for numerical methods?
See, so numerical method, right? All the CFD softwares or FEA softwares, these are built on numerical method. Like for example, CFD is built on finite volume method, right? And mostly stress analysis software are built on finite element analysis method. These are very much similar to finite difference method with different levels of complexity. Now, what is the underlying principle? Why do we use finite element or finite volume or finite difference method? Is basically all these problems are non-linear, right? So imagine when you break down that non-linear problem into very small parts, basically what you're doing is you're stitching small linear lines together to simulate the non-linearity, right? And that's why numerical methods help you solve non-linear problems. So for example, if you want to solve a Navier-Stokes equation, it's in its original form algebraically, there is no solution till today. Like for example, turbulence problem is still not solved. Algebraically, it is not solved. What people do is people do a lot of assumption and then try to solve it. Or people use numerical techniques. What is numerical techniques? Basically, you break down the problem into small components so that your problems become linear, and linear is easy to solve. And then you again aggregate these scores, linear scores, to find the final score. Now, assumption, like for example, in CFD, which I talked about, the flow inside a plane tube, right? And I try to replicate the output that is coming from CFD with the which we have learned in our fluid mechanics textbooks, right? Fluid mechanics textbooks, what we learned, that when my Reynolds number is less than 2000, my flow is laminar. And for laminar flow, if my tube is plain tube, assuming there is no under no slip conditions or whatever that condition, I don't remember. If I am taking a plain tube and my Reynolds number is say less than 2000, my flow is laminar, then my friction factor would be 64 by RE, right? Now the assumption is my flow should be fully developed, and this is one of the assumption. Now when you are solving any numerical, you are trying to simulate using CFD. If you are not allowing the flow to be fully developed, you're not going to match it with what we have written in fluid mechanics textbook, right? I'm just giving you one example. Similarly, there are many examples, right? Like for example, if I am simulating boiler, or I am designing a boiler, imagine, forget about numerical techniques for now. I am designing a boiler and I have taken I need to consider air, right? And So humidity of air in Pune versus humidity of air in Kolkata was going to be different, right? In Pune, you would have humidity of say 40%, 30%, 50%. In Kolkata, you will have humidity of 90%. But am I taking all the conditions while designing the boiler? No. So that is where operating conditions could be different. Now, there are multiple stages, what you are seeing on the screen, right? In design stage, I would take maybe some finite number of conditions to design a boiler, to design a particular equipment. Then in simulation stage, which we are talking about, numerical techniques could be finite volume, finite difference. There, I can run it under different scenarios. But again, I cannot do infinite scenarios, right? There is always a cost to what you do. So I can do some finite number of scenarios. And whatever finite number, it can be even maybe 2,000 simulation or 20,000 simulations. Can I assure that I have run it for each and every possible combination that is going to occur in real life? No, it cannot. But you can at least do some sort of simulation and come up with some combination of parameters to run that particular equipment, whatever that equipment is. But now when you go to real world, that time you are collecting real world data under different operating conditions. And that is from real world. And are you collecting each and every data point? No. Again, AI also has a lot of assumptions behind it. But if you try to build a model and if you so that it's mostly statistical thing. It's not nothing to do with domain. So you have to ensure that your model is not overfitting. You have to ensure that model is not underfitting. You have to ensure that there is no pattern in your error, right? Those your guys are all from research background. You're all faculty members. You would know, right? Even if you are building a regression model, you do a lot of robustness test to fully cover all the aspects of regression model, that it should not, your error should not have a pattern and all that. Similar principle applies for any ML model also. So once you have built a model, even though if you have not measured, say for example, there are 50 process parameters in my machine, but I have sensors only for 20 parameters. So I will not be able to measure other 30 parameters. But can I use only these 20 parameters to build my ML model? Yes, I can. The effect of other parameters will be in error, right? But even if I get an accuracy of say 60% with these 20 parameters, still I have understanding of 60% of the cases. I may not be able to achieve 100%, and no probabilistic model can achieve 100%, frankly speaking, even if you get 50 parameters, right? So there are two ways of looking at it. If I didn't have these data-driven models, anyway, I am only relying on my heuristics. But now, because I have a data-driven model, even though it is say 60% accurate, for the sake of it, let's say accuracy is my metric, still I get to understand 60% of the scenarios intuitively, right? It's not exactly scenarios, but 60% of the cases. And I can take much more informed decision along with my heuristics experience. So assumptions are always going to be there. There would be some known assumptions and there would be some unknown assumptions. There is a book called Economics of Artificial Intelligence. Everyone should read that. And again, it's not a technical book. It's a very generic book. How do you approach and understand AI problems, right? So it talks about known knowns, unknown knowns, known unknowns. Again, this might be a confusing word, but basically what it is talking about, there are few things which we know which are missing, but there could be few things which we don't know that have been missed, right? So even then, we can build an ML model or we can build a data-driven model. As long as you know how to run these models and how to do the robustness test, you will get some understanding of different scenarios, which can be augmented with your heuristic experience or science experience or science knowledge or domain knowledge. And you can improve the efficiency of underlying equipment, or you can achieve the objective that you're looking for. So that is very much possible. Yeah. Any other question? Yes.
Thank you, sir. One more question I just want to
Yes.
ask. Whenever we are
Yeah.
checking for a parametric and non-parametric model, any.
Yes.
So at time, after getting the result of non-parametric or parametric, it is very essential to identify the assumptions like independent and the seasonal
Correct.
parameters
Correct.
are very important for that. So
Correct.
after getting the result, that is knowing that these assumptions are important. For that purpose, any graphical representation or EDM is available for checking the assumptions in graphical way.
No. So see, graphical is again because you're manually looking at those graphs, right? So basically, parametric and non-parametric is nothing but whether it has a distribution or no distribution, right? Now, imagine if you are looking at 100 variables, right? Out of which uh, uh, some are categorical variable and some are, say, numerical variables, right? 100 variable humanly you cannot consume. Even though there is a graphical representation, definitely EDA you can do a lot of different plots. But instead of relying on EDA, there are different ways and means to understand the distribution, like the KS curve, probability stability index, population stability index, and then there are many techniques through which we understand the distribution. Basically, what our objective is, right? If I am building a model with whatever constraint, whether I have taken into account each and every variable or not, whether it's a parametric or non-parametric model, doesn't matter. Whether I have taken into account each and every variable, in no case I can take into account each and every variable. Practically, that is not possible at all. So still, can I build a model? Yes, I can build a model. Now, the point is, I'll give a business problem analogy to this because everybody can understand that. Imagine I have built a model to understand the credit score, right? And my variables are, say, age, geography, and income. So let's say only 3 variables, right? And in my historical data, I have income of, say, 1 lakh rupees to 10 lakh rupees. In my age group, I have readings of, say, 25 years of age to 40 years of age, right? And then geography, I have, say, only Maharashtra readings, right? Now, most important factor when I build a model, and if I get a new case, I need to see whether my new case lies into the distribution of my input training data or not. If it is not, then my confidence level goes down, right? That's what my confidence interval is. So imagine my model was trained on 25 years of age to 40 years of age. I'm taking one variable in isolation. In actual practice, it is not in isolation. There's a 3 variable in combination which has helped me to build a model. Now let's look at only one variable. So I have trained a model for age group of 25 to 40 years, right? But my new reading, I got a new person whose age is, say, 50 years. Can I use the same model to get my credit score? No, it won't be. Even though I can build a model, I can use that model to get the credit score of this new person also, but I won't be confident about my score. Why? Because the underlying input distribution, the new data point does not lie inside my distribution. So how do I check it? There are means to check it, right? You can have the PSI score for individual variables. How do it for aggregates? How do you do it for aggregates? There are custom way of doing it. Again, so what we are getting into is statistics, right? So what essentially I am saying to your question is, EDA, there are many graphs that you can look at. But when we are talking about data-driven model, we are talking about that humanly when you are not able to comprehend, then you go for data-driven model. So instead of relying on BI dashboards or EDA, we should have some sort of statistical technique to get those scores, because then there is no limit on how much humanly you can comprehend, right? Because you get an aggregate score of, so imagine you have 100 variables. You cannot do EDA and you visually check each and every variable and the combination of variables. That's where we started with. That's where your data-driven techniques or data-driven models and data-driven scores helps you identify those and nullify those assumptions and tick those necessary check marks and necessary robustness checks. Right?
Okay, sir. Okay.
Yeah.
Which one is, sir? Multivariate model or univariate model is best, sir? For
multivariate, definitely multivariate, right?
Yes.
Univariate, generally now in today's world, univariate is only used for time series models, or rather forecasting, which is a time series model problem, right? Else, every other problem is multivariate, because when we are talk about whatever predicting, even time series also is multivariate, but still till today people use univariate. But other than that, any other problem which is cross panel data, you will end up using multivariate, because there are a lot of other variables which take into account when you're predicting something, right? So why to lose that? And if you have data, you should use it. So multivariate is always better. Only if you are going for time series, univariate can also work. But other than that, it's always better to have multivariate, because it gives you an idea of what is the effect of this parameter on my objective variable, whatever that variable is. Even say, for example, the best use case of time series is stock market forecasting, right? So you can do it univariate also. But now if you have, say, market outlook data, some news data, Can you convert that to a numerical field? Yes. For example, there is a news that has happened yesterday. Can I impose the effect of that variable on my stock market price? Yes, I can do that. So that's where a multivariate comes into picture, and it's always very powerful.
Okay. Thank you, sir. Thank you.
Yeah, yeah. Anybody else? Any questions?
The participants, you can also post your questions in the chat box.
The AI, right? You might be hearing about AI. There is a lot of hype and noise about AI, right? So AI, you can do a lot of courses, right? There are n number of free courses available. There are n number of paid courses available, and very good courses available. But AI is best learned if you have a problem statement. And it can be as simple as even predicting scores of your students. Again, this is not a good problem statement to have, but I'm just giving you an example. It can be a very simple problem statement, and not rather not to predict student score, but something else. But if you try to use it for your problem statement and then try to look at different scenarios, it is learned well. Because even I teach AI in few institutes. What I see is, and I talked about this persona, right? I can always start teaching you ML or AI with linear algebra also, right? Or maybe someone starts teaching AI with Python, right? Or someone maybe start teaching AI with use cases. It's better to start with use cases, and use cases is a very common word used in industry. It's basically problems, actual problems, business problems or domain problems, because that will help you be more practical on how AI will be used, and you will be able to relate to, and you will be able to verify also. Like for example, in CFD, we always, and why I'm talking about CFD, because CFD has been around for a long time. CFD, STAD, FE analysis, stress analysis, it has been around for a long time. But we all know these softwares, if you put in junk in, if you are putting wrong boundary condition, it is going to give you junk out. Similarly, in AI ML space, if you put in junk in, you are going to get junk out. So how do you verify? Using your domain knowledge. So domain knowledge doesn't go anywhere. So that's why if you pick up some problem which you understand thoroughly, which is a part of your domain, whether it's mechanical domain, civil domain, electronics domain, and then try to use different techniques on one problem, whether you are using logistic regression, linear regression, random forest model, you'll be able to understand the space very well, instead of wondering here and there, because AI is getting overwhelming, right? Every 2 months you will find something else is coming up. And it is very interesting space also, because you can, as soon as you start relating it to your practical problems, you will find it very useful. Some or the other day, everybody will start using it anyways. So that would be my 2 cents on how you should start reading and learning and getting some sense of AI, or say for that matter, that is our topic, right? Emerging technologies. Because once you understand where and how to use it and where not to use it, that is also very important. Because nowadays people will talk about that everything can be solved using AI. That is also not true. There are many problems which does not require AI, right? So once you start relating it to your problem and your domain, no, so that time you will be able to appreciate the power of all these data driven models. Yeah, I think there is something in chat. Okay, no question. Anybody else, right? This would be, so if you ask question, then you'll be able to appreciate more on this topic, right? I can keep talking about AI because AI is very vast. I can even touch upon, say, how LLMs are used, how chat GPT used. But if you try to relate it to your use case, and I may not be expert of each and every domain, or rather I am not expert of each and every domain. I have done mechanical engineering and I can talk about it, but nothing apart from that. But I can tell you from a data-driven side or AI side, I can tell you how your problem can be solved, whether it is whatever domain you are coming from, whether it is civil engineering, mechanical engineering, electronics engineering. So if you have any questions, feel free to ask.
Mr. Rahul, there's a question coming.
Yeah.
Like you pointed
Yes.
out the importance of data-driven model.
Yeah.
Reference to that, if we see that other than forecasting, like how can AI and data analytics increase the India's renewable energy navigation and grid management system? Like we are shifting from we are trying to shift in the new renewable energy world. So how can this
Correct.
analytics help us?
Correct. So I'll tell you 2, 3 examples which I came across practically, right? When we talk about renewable energy. Uh, and one is more on a business side, as trivial as setting up a solar power plant, right? And it is combination of both uh, a business transactional problem and also a domain problem, right? So imagine if you want to choose a site and if you want to even decide on what should be the capacity of my solar power plant. And mind you, when we talk about even the capacity, right, there are different contractual obligations and different policies that you need to cater to. Government has different policies and different conditions and different rules for different capacity of power plant, different area of solar power plant, different geography of solar power plant. So if you really look at this problem, even when you decide to install a solar power plant, imagine if some of you start a business of setting up a solar power plant. It is not as straightforward that I just decide and go and install it in Rajasthan or some maybe in Sambhajinagar, right? There are different rules involved. Now imagine if you want to navigate through these rules and understand what could be the best combination of geography, of capacity, of n number of or maybe type of equipment that is used. From where do you procure your solar panels? Uh, this can be very well solved using combination of LLM and ML today. How? LLM will help you navigate through all these rules and convert that to some form of structured data. And once you have that some in everything into a structured data space, you can convert that to an optimization problem. So, for example, if you are optimizing in on cost, I want to say my budget is say $10,000. I'm just making it up, right? I can optimize it for part, but to even formulate that problem, I need to convert all this unstructured data into structured data. I'm right now giving you a business scenario example. I'll give you the domain scenario example also, right? So whenever we talk about at the end of the day rates, for example, if you are doing even renewable energy and there are a lot of subsidies available for anything to sustain, it has to stand on its own. It's not like subsidy is going to be for the forever, and it is not like if I'm not making money out of that as a business user, right? Whoever is setting up that plan, any big company setting up that plan, everybody is running a business, and finally at the end of the day they should be able to run that business efficiently, or else nobody is going to do that. So there are uh, energy economics in this particular business problem, and there is also money economics, right? Actual economics in this problem, and how you combine the information of both and get to your optimization. And I found that this problem statement is very tricky. Those who are installing solar power plant, they navigate through all these rules, right? So this is one use case wherein it is more on the uh, installation side, right? And now the second part is how do you do optimization at an operating level? Imagine I have a solar connection in my plant. I'm just creating a hypothetical use case, and then I have a diesel generator from which I can get electricity in a plant, and I have a solar connection also, and then I have maybe third source of energy. So if I want to, at the end of the month or at the end of the year, my objective function is I should be spending less cost. So what, let me tell you. So what is an optimization problem? There are 3 things in optimization problem. One is objective function. Second is decision variables. Basically, what are the variables which are playing role in a particular problem? And then there is constraints, right? So when I'm looking at combination of different sources of energy to run my plant, which are running on diesel engine, which is running on solar, and which is running on uh, say grid electricity, right? So there are multiple variables which plays into role. And if I want to look at the combination, because as a business person, right? So at the end of the day, no one is doing charity in practical sense. People talk about a lot of things, but at the end of the day, it should be economically viable also, right? So if I am doing optimization on the usage of this particular 3 sources of energy. One is grid, one is renewable, and one is diesel generator. Are different operating condition inside my plant. Again, it's a data problem, right? Can you apply any scientific rule to this? No. You cannot, right? Because there are too many domains involved, too many fuels involved. It become a data problem. Now, can you build a model on the day one? No. But once you have enough reading for 6 months, then you can run such problems with your objective. An objective could be combination of cost plus energy consumption. I will put some hard constraint that my energy consumption should not be more than this, or my maybe I will go forward. Instead of energy consumption, I will put an hard constraint on carbon credits that are being calculated for the usage of combination of solar and diesel generator and grid electricity. And I'll come up with some combination that this plant in shift 2 should run on solar, but this plant in shift 1 should run on diesel generator. This is my combination which I get to achieve my objective, where my revenues are also good and my energy consumption is also less. There are n number of problems, frankly speaking. If we really go to real life problems and practical problems, there are n number of problems that can be solved using data driven models, because you cannot formulate scientific equation for each and every problem, right? In isolation, I can have scientific equation for one part of the plant, or at a plant level. But when we talk about so many dynamic variables which are coming from different sources, that's where data driven problem comes into play, and it helps you achieve your underlying objective. So it can be used even during decision making of setting up a solar power plant. It can be also used during operations of a given plant, which can have multiple energy sources coming from renewables and non-renewables. I hope I answered your question.
Yes. Questions from participants?
Is this the last day, or we have something tomorrow also?
The last day.
Oh, so last day, last session. Good,
No.
then you should ask few questions. We have last 12 minutes, 13 minutes.
Yes. Mr. Rahul, can you
Stop
please
sharing.
put down some, like you mentioned, best courses on AI? If you could mention it, sources.
Yes. So I would mention, see, there are many, but it is better to follow one particular course structure, right? So I would recommend, say, deeplearning.ai is one of the website, deeplearning.ai, which is run by Andrew Ng, who is a pioneer in AI field. So you will find courses right from machine learning, statistics to LLM agents, everything at one place. And they have a combination of both free and paid courses also. Because when you start, even if you bother about learning AI, and if you go on YouTube, and you will get overwhelmed with so much of material available, right? So better to stick with one thing. So I would recommend deeplearning.ai, where you will find everything, and stick to that, because it will give you a good gist of what is coming up, what are the technologies available, and once you know about it, then you should start relating it to your day-to-day business problem, rather domain problem, science problem, or even your operation problem of your education. Yeah.
I request all the participants for a group photo. You can please put on your camera if it's possible for you. So we'll have a group photo with our guest, which is generally done in face-to-face, but this is the solution we have, modern solution. I request the participants to please on your cameras.
Okay, take it.
Thank you.
Okay.
That was indeed a great session, Mr. Rahul. And when you said energy saved is energy generated, that's the most important thing we need to follow, because we can see a lot of wastage of energy in and out, in our houses, in our offices, everywhere. So if you could save that energy, we are actually generating energy. That's very true. It was really an informative, knowledgeable session. So I now request Professor Munde ma'am to please propose the vote of thanks.
Thank you, sir. Thank you so much. Thank you, Mr. Rahul Khara, sir, for an extremely insightful and thought-provoking session by you on the topic navigation energy challenges, the role of emerging technologies in India's sustainable future. You really take it in hands-on mode. That is really appreciable. The highlight of the session, it is hands-on mode. Also, you take all the questions very sportly and answered it in well. Congratulations and thank you so much. Your perspectives on how AI, technology innovation, and sustainable energy practices it coverage to shape India's progress were truly eye-opening and inspiring. We are really grateful for the way you connected real-world challenges with emerging technological solutions, making the session both practical and forward-looking. Thank you. Thank you so much, sir, for sharing your valuable time and expertise with us. I would like to take a moment to thank all the participants for your active engagement, thoughtful questions, and enthusiastic participation throughout the day. Your curiosity and interaction, it bring a real energy to this FDP. Thank you all the participants. Yes. As a special word of appreciation to our respected principal, sir, principal of this institute, Dr. Vadikar, sir, and secretary of the People's Education Society, Mumbai, coordinator, Dr. Deepak Kakade, sir, convener of the program, Dr. Siddharth Tundirwade, sir, co-convener, Professor Prashant Pandit, sir, organizing team, all deans, and heads of PS College of Chhatrapati Sambhajinagar, all the faculty coordinators and technical support members who have worked tirelessly behind the scenes to ensure the smooth conduct of this program. As we come to close of this Day 5 ATAL Online FTP program, we conclude this day by those we carry forward a wealth of new ideas from greener rocket propellants to smarter energy systems, all pointing towards a more sustainable and innovative future. Finally, we hope today's session sparks further teaching, research, and collaboration on sustainable propulsion systems. Thank you once again, Dr. Kumbhakarna and Mr. Karat, sir, and all the participants.